So we come to our first speaker. Our first speaker grew up in Shenzhen, China, in southern China. Went to Nanking University and then joined and studied physics there, and then joined us here at Caltech as a PhD student in the astronomy department. She is in her final year of graduate school. In a year's time, she will be a PhD. She will be a doctor. And she's going to talk all about, well, first of all, her research is all about galaxy evolution throughout many phases of its evolution. And tonight she's going to talk about the early phases of galaxy evolution and what we've learned about galaxies in the early universe from the James Webb Space Telescope. So please welcome Zhuyun Zhuang.
Okay, so can everyone hear me okay? Do I need to increase the volume a little bit?
Just hold it closer to you.
Okay, I'll try to shout for my presentation. So yeah, are you ready for a really cool story about the largest space telescope people have ever launched into the space, the James Webb Space Telescope, or JWST? First of all, this is a picture showing the real JWST before it was launched into the space back in, I actually don't really know when this photo was taken, but definitely before it launched in the Christmas of 2021. And so this is, the largest space telescope people have ever made. It has a primary mirror of around 21 feet, and basically making it 6 times larger than its predecessor, the Hubble Space Telescope. And basically you can see, how large it is compared to the people standing below it. And because this is a really, really powerful telescope and also very expensive for sure. And when the first data release arrived around July 2022, just roughly 2 years ago, there were a lot of very, very surprising results for many things. And the most astonishing one is probably on the galaxies that was formed in the very early stage of the universe. And some of you may have actually read those very sensational news on the media, saying that the discovery from James Webb Telescope has broken our understanding for the early universe, and scientists were panicked, need to make up a completely new theory to explain the universe. So for this talk, I'm going to walk you through for what has happened in that time, what astronomers discovered, and after 2 years of this big discovery, what has ever changed ever since. So the first question is, what is a galaxy? It is a very familiar term for me, but probably not for a lot of people in the audience. And the video here basically shows a fly-through view for the galaxy. We can see that there are a lot of diffuse things around the galaxies, and this is the gas. The gas. And we can also see that there are a lot of dark patches in this video. So these are the dust lane, the dust in the galaxy, and those isolated bright spots are the stars in the galaxy. And finally, we have something that cannot be seen in this video, but still is very important, which is the dark matter. They cannot be visible through the light, but they can contribute a lot to the gravity that holds the galaxy together. And so what is special about JWST? It is very powerful, and with unparalleled resolving power. So basically, make it very good at detecting those very, very distant galaxies that were formed in the very early phase of the universe. So the plot here basically shows our current understanding of our cosmos. We know that the Big Bang, which is shown in the very right end of there, happens at around 13.7 billion years ago. And that is really where everything started to happen. And roughly around a few 100 million years after the Big Bang, the galaxies, the very early galaxies, the first galaxies started to appear. I know in astronomy, we usually say this is a really short time scale, even though I know a few 100 million years sounds like crazily long if we compare that to our own life. But you need to keep in mind that the universe has a history of more than 13 billion years. So that by comparing these two time scales, that is indeed a very short time period. And so in order to really have a full understanding for our current universe, we really need to know, what happened in the very early stage. basically by looking at those very faint galaxies that can only be studied by the JWST. And there's also another jargon I want to mention here. In astronomy, whenever we talk about those very distant galaxies, we don't use miles, kilometer, or whatever whatever metric that you are familiar with, because the universe is so big. And in reality, we use a term called redshift to describe and to quantify the distance of those galaxies between us. And now we know that the universe is expanding. And actually, the further those galaxies are, they are moving actually at a faster speed compared to the nearby galaxies. And by doing that, basically the light emitted by those very, very distant galaxies got stretched out a lot to the longer wavelengths due to the Doppler effect. So this is very similar to the pitch change you can actually hear if there's a police car that is approaching you, which is probably not good, or leaving you, and you feel very lucky about it. And for most, in our case, the police car is indeed leaving us, so don't panic. And we can see another example here. So in this plot, we can see that the earlier galaxies, which is here, all the features is moving, to the redder part of the spectrum, to basically to the longer wavelength compared to a nearby star, a nearby galaxy, or a local reference. So in this case, astronomy basically would use the fractional change in these features to quantify the distance between those objects and us. This is a really complicated concept. You don't have to really fully understand it. Just keep in mind, if a galaxy is at a very higher redshift, it means that it is very, very far away from us, and they were formed in the very early universe compared to the nearby galaxies that were formed much later and at lower redshift. So the video here shows the evolution of the galaxy size as universe is getting older. So we can see that in the earlier phase, there are just very tiny galaxies showing up in this simulation. They are just like those very tiny dots. There are indeed like some massive galaxies, but not many of them. However, if we wait longer, and as the universe is getting older and older, we can see that more galaxies and also larger galaxies started to appear. This is really what we know as a galaxy growth, because galaxy is kind of like human being. You have to be in the infant stage here, and then go to become a toddler, and finally become the adult. So this is really our general understanding of the universe. And because of that, basically the current model predicts that in the very early stage of the universe, all the galaxies should be really small, and we should not really discover those massive galaxies. However, this is not what JWST has found. So what did JWST discover? It discovered way too many massive galaxies in the early universe, which means it's completely different from what people expected before the JWST launch. And that was a big moment for the astronomers, because everyone is like, okay, what happened? Do we need to make up some new theory to account for all these very massive galaxies? Do we just do everything wrong in the past many, many years? And basically what astronomers found is that there were several group of astronomers found really, really mature and massive galaxies in the very early stage of the universe. And among these big discovery, these 6 galaxies is the most famous one. So these 6 tiny red dots are showing here. So these galaxies were found to be at around 500 to 700 million years after the Big Bang. But they have the masses which is pretty much as massive as our home Milky Way. But we need to remember, it took around 13 billion years to form the mass, to form the stars in the Milky Way, but it only took just a few hundred million years in these galaxies to form the same amount of star. So that's a really, really drastic process, which means the star formation in these galaxies probably happened, I think, at around 30 to 30 times faster than our Milky Way. And this is totally not what the former model predicts, and people just got really panicked. But one thing we need to remember is that before just coming up with a completely new theory to account for the abundance for these unusually massive galaxies in the early universe, there's another question we need to think about. Are they really that massive? And are they really that far away as people thought in the beginning? And to answer this question, we need to actually go back to the very beginning. How do we really measure the mass and the distance for a galaxy? So in astronomy, we make use of spectrum. So basically, if you shot a light through a spectrograph, either a prism or prism like this triangle, you can split a white light into a spectrum. And spectrum basically can just tell you the light intensity at different wavelengths, kind of like, I think the closest example is kind of similar to the rainbow you will see after the rain. And we do that, but instead of looking at the rainbow, we look at the galaxy. And the plot here basically shows the spectrum for a galaxy, for a very distant galaxy, shown by the white solid line. Oops. This is a very complicated plot, so you don't really need to know all the ingredients unless you wanted to study astronomy and also, do research on galaxy. But there are several key features that we need to pay special attention to. The first one is the first break happening at a shorter wavelength, so, part of here. And this is really what we call Lyman break. And the first break at a shorter wavelength is very sensitive to the distance of the galaxy. In this case, if we can measure where the break happens, we'll be able to tell how far the galaxy is away from us. And there's a second break, which has happened in the center of the plot here, which we call Balmer break. So the strength of the second break with the second drop is very sensitive to a lot of information of the stars sitting in the galaxy. For instance, how old are those stars and when did they form? And finally, we need to really measure the overall level of the spectrum. Because imagine that you are looking at two things at the same distance. A brighter galaxy would definitely be more massive. In that case, the spectrum is at a higher level. But in reality, we don't do spectrum because it is very, very expensive and we cannot really do it for every single galaxy. Usually the first task in astronomy is actually to take multi-band images for those galaxies. And this is quite like, going to the hospital and taking an X-ray photo, and people will compare, the doctor generally will compare the X-ray photo with your hand to figure out whether there's something wrong with, your health condition. And so we did that same in astronomy. So instead of just taking the spectrum, what the astronomers do is usually just to use different filter, basically just summing the spectrum in different window, showing by the different boxes in the top panel here. And by doing that, we can actually get a series of multi-band images showing in the bottom here. And if we look at something, the leftmost one, we can see that this is really the region where the Lyman break falls. And because of the Lyman break, the galaxy just completely disappear at the shortest wavelength. And if we keep, increasing the redshift of the galaxy, more and more images start to disappear at the shorter wavelength, and then they only show up on the longer wavelength. So this is really just like a very general idea of how astronomers measure the distance for the galaxy. And that's also how JWST, those massive galaxies in JWST was found in the beginning. So people were doing a lot of machine learning or eyeballing the data or all those fancy algorithms to see, to find these galaxies that disappear at a shorter wavelength, like you can see in the leftmost image here, and only show up in the longer wavelength. But definitely we do it in a much more decent way rather than just eyeballing the image and say, hey, this is a high redshift galaxy candidate. In reality, we will compare the observed images at different wavelengths with all those galaxy models of different galaxy properties. So we need to make assumption on how far the galaxy is by measuring the redshift, how many dust are in the galaxy, what is the mass of this galaxy, and how did it form all the stars. So this is a very complicated process, and all the parameters are highly correlated with each other. So in this case, if we happen to mess one measurement wrong, we pretty much messed up every single thing. So what we can mess up, this is actually the funny part, because after 2 years of investigation, astronomers have figured out that there might be other ways to explain the observed images rather than making the galaxies supermassive. The first one is the dust. So if you have ever been to Joshua Tree for a stargazing event, or have ever seen the real Milky Way, you will notice that there are some dark patches in the Milky Way, the things here. So this is the dust lane in the Milky Way. So for our whole Milky Way, we do know that there are a lot of dust in it. And these dust can suppress a lot of light, especially for those coming from the shorter wavelength. So how does that really affect the spectrum? So in the right plot here, we can see that if a galaxy doesn't have any dust, the region near the lemon brick would be very similar to the dashed line there. But if a galaxy has a lot of dust, it will suppress, this dust is very good at suppressing the light in the shorter wavelength and basically making the spectrum more similar to the solid line over there. And we know, the location of this brick is essential for us to determine the distance. And if we get the distance, the dust content in the galaxy is wrong, we will just, basically mess up with everything. This is very similar to the case that, let's see, imagine you are driving in a very foggy night. You will definitely notice that the headlight of all those cars become dimmer, probably, dimmer a lot. And if you don't really know that there are a lot of fogs between you and other cars, you would naively think that there are many, these cars are just really far away from you. And because of that, you probably will forget to hit the brake, and finally, something bad happened. And that's kind of similar to the astronomy here. If we forget there's dust, or if we get the dust content wrong, we forget to hit the brake, and we get everything wrong. Another thing is the star formation history of a galaxy, or more like the working schedule for the galaxy. Like human being, again, galaxy cannot work every day. We have to go to lunch, go to dinner, take a shower, take a nap, and also take the weekends off. So galaxy apparently cannot work all the time, because you will get tired a lot soon. So sometimes the galaxies is pretty happy, basically for many stars in a short period of time, because it's super energetic and want just to have a lot of stars present in the galaxy. But sometimes the galaxies get really exhausted and just wanted to take some time off. By doing that, they just stop forming galaxies, stop forming the stars. So how does that really change the observed light? So this is a plot I took from the fire simulation, where in the left panel, this is a galaxy that was basically the picture of the galaxies at higher redshift, the earlier stage of this galaxy. And at that time, it was forming the stars really rapidly, so it's really bright. But later, if we waited for a bit, the galaxy still have star formation going on, but it just got a little bit tired and only want to form a little bit stars at that time. And even though the galaxy does become more massive, in the right image, it becomes dimmer. So if you really don't know what is the working schedule of the galaxy, you just messed up with the mass measurements. So imagine that you are the boss and you have 2 employees. The first one is super lazy, basically taking the day off every day. But for whatever reason, they were so smart that they happened to keep work crazily whenever the boss visits the office. And we have another employee who is really hardworking literally every day. But they need to take rest too, so they just take a nap whenever you visit the office. And if you're the boss, apparently you will think the lazy worker, this one, is very hardworking and really productive, and really productive, has really high productivity, because that's what you observe. But in reality, apparently the hardworking one is the key. So you really need to know what is the working schedule of your employee to figure out which one is more productive. In other words, astronomers, we also need to figure out the working schedule for galaxies, star formation history, to figure out which galaxy is more good at making all these stars. And another thing is the initial mass function. This is a kind of a complicated concept, but basically this is the mass distributions of the stars within a galaxy. So from the observation of our own Milky Way, we do know that we cannot really form stars at any mass randomly. Instead, Milky Way is much more efficient in forming those very low mass stars compared to the high mass star. And fun fact, if in our own Milky Way, I believe there are probably just less than 5% stars that's more massive than our own sun. So basically, there are a lot of stars, like roughly 200 stars. Well, the number doesn't really mean anything. This plot doesn't imply that there are only 261 stars in the Milky Way. This is just like, a cool animation. But this is just like, the general distributions in the Milky Way. And astronomers decide to apply the same initial mass function to every single galaxy, whether they are distant or not. And that actually can be a problem, because imagine that maybe those galaxies in the early universe is very, very good at forming the massive stars. So instead of only have one star sitting in the most massive being, maybe there are 100 stars sitting there, and we only have 100 stars in the lowest mass being. And that can really change the inferred results a lot. And if we do take the variation in the initial mass function into account, the inferred mass for those galaxies will no longer be that massive. And finally, there's actually one component that we are missing in the picture here. Galaxy does have another thing that I didn't really mention earlier, the black hole. So every massive galaxy would have a black hole sitting in the center of it. For most of the time, the black hole is just sleeping, and in that case, it doesn't really tell you anything. You will not be able to observe it through, using the electromagnetic spectrum. But there are always some cases, the black hole want to be kind of active, and basically start eating all the surrounding material around it, just like getting hungry and keep eating all the things. And by constantly eating the surrounding material, it can really form, an accretion disk made up by these stellar debris and also the gas and all the other things, and also a dust rain. And sometimes if the black hole is really active, it can also have the jets. And all these components of the active black hole can also contribute a lot to the observed light of the galaxy. And I think, when the JWST data was released, people basically just forget, well, some people apparently probably, just forget that the possibility of having an active black hole in the center of these galaxies. And because of that, they just ignore the contribution from the black hole. And funny enough is that I think probably a few months after those discovery for the massive galaxy candidates, people finally get the spectrum for those targets. And from the spectrum, they know that those galaxies indeed have a very active black hole sitting in the center of it. And with the black hole, in the active black hole in it, those galaxies doesn't really need to be that massive. So going back to the original question for my topic, the JWST really break our understanding of the early universe. Are these sensational topics really the case? Well, after 2 years, astronomers have found that there are many, many other possibilities, and some of the possibilities are actually the case. And with all these uncertainty taken into account, at least at the moment, I would say, it hasn't really, changed anything. And people are still actively working on it. And yeah, I hope, by the end of the talk, if next time when you really read these news, you can remember that maybe something is different. And that's all I have for today. Thank you.
So we can take a few questions from the audience.
What causes black holes to go to orbit, and what causes them to become active and start pulling their, surrounding matter like
So the question is, at what scenario the black hole becomes very active, and at what scenario the black hole becomes is sleeping? First of all, I guess I can only say from an educated guess because I'm not really 100% sure about it. But I think the black hole can be it's because of the accretion.
We don't really know the answer. It depends on the environment. It depends on the amount of material that's falling onto that black hole at a particular time. It depends on the formation and the structure of the accretion disk, which is the kind of disk of material that's swirling down onto the black hole itself and how quickly it's feeding. But this is a very, very active field of research, and there's actually one of the pub trivia questions is going to be related to this.
Yeah, and also like in some cases they can switch mode, so they can like so they are not sleeping all the time, but also they are not active all the time. Okay. Okay, so like the question is, whenever I say dust would absorb the light, and like how does that really make it work? Oh, well, this involves in a lot of like very complicated molecular physics, and I guess for the time limit, I'm not going to really go very deep into it. But this is very similar to the when I say it suppresses light, it only suppresses light in the rest frame optical, which is really what we observe with JWST, rest frame optical to rest frame UV. And the light would, and also the photons, which is the thing, the particle that carries the light, would actually re-emit this light at a longer wavelength. I don't really have a picture with me at the moment, but if you Google the infrared image of the Milky Way, you can see that the Milky Way actually becomes really bright in the center compared to the typical optical image that we usually see in those stargazing events or astrophotography.
Yes, how far back in time is CMB relevant? How far back can we observe that, as opposed to ultraviolet and other spectrums?
Okay, the question is how far the CMB, the cosmic microwave background, is relevant to us. I only know the number from the redshift, which I believe is around 1,000. Is that correct? Yeah, so it's like very, very far away. And JWST, to my knowledge, I know there are a lot of cosmologists sitting in the back audience, so if I say it incorrectly, please correct me. I believe JWST is not really sensitive to the cosmic wave background, and what they really need to do is actually go to even longer wavelength, which is the radio telescope, because that's like basically all the signal is coming from the cosmic microwave background.
So the question is, you were explaining potentially these massive galaxies at early time as having supermassive black holes in their center and the active galactic nuclei that they cause, but doesn't that indicate that doesn't that introduce a new problem that you have very massive black holes at very high redshifts in the very early universe? And the answer is yes, it does. It is another problem, and it's something that is an active field of research that people are trying to understand. Okay, let's thank our speaker, Zhuyun. Excellent talk.